she sells seashells. Don't forget to moisturize, guys. It's pretty important. Hi everyone, hope that you all are enjoying the holidays. I know I am. I have one last night before, loads more family time. I love him so, but loads more family time, and then, things start up again in January. So tonight's the last night that I have left to just, putter around in my favorite place on earth, which is the lab. I got a lot of things, a lot of little side projects going on, and maybe I'll take you through each one, see what people are interested in. But one thing that I'd really like to try is doing maybe more educational content to, pass along some of the skills that I've learned over the years. I don't know how much longer I'll be in academia, maybe not too long. I think next semester will be my last semester TAing, and then it's off into the real world from the embrace of grad school. But it's exciting. It's exciting and anxiety-inducing times. But yeah, so educational stuff. I figure I'll go through basic molecular biology techniques that I think every scientist or biologist needs to know. And basically work at it from it's kind of how I like to solve problems. Go through the reverse approach of, what am I trying to do? And then figure out what are the steps that I need to get there. So our first lesson or webinar is going to be about cloning, protein expression. So for example, your boss comes up to you and says, hey, I need so-and-so protein expressed, purified, have at her. And you're just sitting there, maybe you haven't had a lot of cloning experience, and you're just like, okay. Usually when your boss tells you or asks you to do something, you want to figure out a way to actually deploy it. So, your boss comes, or let's say in your head you have a goal. Okay, how do I get there? So we want to clone, express, and isolate a specific protein, let's say a very common biotech requirement. Basically what I'll do is I'll take you as far as I can from A to Z. So we're gonna start at the most basic level of, do I have the right sequence, how to check if I have the right sequence, and then going through the primer design, the cloning, going through gels, and going through, protein purification and activity assays. And, I think it'll be fun to do kind of a real life example. So, one plasmid, that PPN1, and it's a good enzyme to degrade DNA that's been methylated by E. coli. So you can go through a fair amount of it. And the patents have expired quite a long time ago. So we'll actually start from, the idea, okay, we want to make a lot of DPN1, or your boss wants you to make it, whatever. Then, okay, all I have is that idea. We're going to go to the patents. We're going to find the sequences. We'll do what we have to do. We'll figure out the primers to clone it, do all that. I'll hold your hand through every little step, and hopefully people will enjoy this sort of new format. I'm just trying to see what people are into. Yeah, so that's essentially what we're doing today. A little webinar on just cloning a protein and making it go and making some active protein. So this will be a multi-part series. I think it'll probably take 2 or 3 parts, but let's see if you even like part 1. So we have a task, okay, and it's to make lotsa protein, okay? That's what you want, that's what your boss wants, that's, what we're here to do today, from start to finish. And for the sake of an example and a real example, we're going to be cloning, expressing, and purifying DPN1. Okay. And some of you may buy this enzyme, and we happily buy this enzyme as well. But we, did the numbers, and we're spending quite a bit of money on this guy. So it would be good to make some of this protein. And let's say there's a protein that you yourself, as a lab, go through a lot of. Perhaps this can serve as a guide for you, how to get your own. Okay, so our goal is to make lotsa DPN1. So there's a couple of steps that we're going to go through, and first of all, we have to figure out what's the sequence of DPN1. So let me backtrack a little bit. DPN1, it's a protein. Sure, that's exactly what it looks like. So it's a protein. And what it does is it cleaves DNA, double-stranded DNA that's been methylated. That's been methylated by E. coli specifically. So that E. coli does a specific type of methylation to this double-stranded DNA. And the DPN1 can recognize it and cut it into little bitty pieces. And what you can essentially use it for is to reduce the level of background in your cloning reactions, and I'm sure there's a couple of other niche uses, but we go through a fair amount of it. So the first question is, what is the sequence of DPN1? Okay, we have to figure that out. It's, when you're approaching a problem sort of in the reverse way, someone tells you, okay, make lots of DPN1, and you're like, okay, well, what's the sequence of DPN1? Then we're going to sort of do the design, the experimental sort of design. So stuff like cloning, primer design, and then expression and purification. Can you tell I'm not an artist? We're actually going to do the cloning, verification, induce, purify, test for activity, and contaminants. Okay, so this will probably be a multi-part video. To some of you, this may be a walk in the park. This is your bread and butter, but if you're just starting out, I think, the whole purpose of this little workshop is, to hold your hand through all these parts, and then you can adapt this sequence of events to, express most common proteins. I won't go too deep into any of these, otherwise we could be here for years and years. You can teach an entire course on this kind of stuff, but hopefully I'll give you the sort of framework that you can use to adapt to purify some of your own useful proteins, either for your research or to save a bit of money. That's the end goal of what I'm doing. So first things first is we need to actually find out the sequence of DPN1. We know what it is, what it roughly does, but where do we get the sequence? So some of you may want to go immediately to PubMed nucleotide database, and I mean that's a valid sort of approach, but I found that you'll be looking for a while unless you are very good with PubMed and using the different filters. Then this is actually a little bit slow. We'll use PubMed at some point to verify the sequence, but one of my favorite sources for these sort of commercial industrial enzymes are patents. So we're going to go find the original patent for DPN1. I already know it exists. I've sort of gone through this process already, but I'm just walking you guys through it from start to finish. So we're actually going to go through the patents and then probably verify it with PubMed. But let's go take a look, okay? So there's, patent law and biological patent law is an entire sort of career path, and people get paid lots and lots of money to do this sort of thing, so I'm not that by any means, but there's a couple of resources which are, useful and available to the common person. And one of the best is Google Patents. Yeah, Google Patents, one of the best. And for non-experts, probably my favorite. Then there's a whole, plethora of other sites. So like you have your American patent searching, Canadian patent searching, European patent search. And in theory, they should all give you the same results, but there are actually advantages to searching through the same patent in different patent search engines, because they can give you different bits of information that you need in your, I suppose, reverse engineering endeavors. So let's start with Google Patents, and let's just do a quick search for DPN1 enzyme. Boop. Alright, so that was pretty easy. Nope. And recombinant plasmids for encoding DPN1 sold. Okay, so let's credit where credit is due, of course. Thank you, Sanford A. Lax of the Brookhaven Science Associates. I wonder where those guys are now. And, you don't want to upset anyone, so you generally do want to look at, where the patents are filed. So is it filed in the US, in Canada, in the EU? And then you want to see the different events that the patent has actually gone through, like when they filed it, whether they renewed it, whether they, did any. Sometimes, sometimes the companies will forget to pay their fees or something, and they get their patent revoked. It's kind of an interesting little quirk, but we're pretty good here because actually it looks like it's expiring today. Isn't that nice? So anyways, it looks like it's finally expiring today, and that gives us a little bit more freedom with what we can do with a plasmid. Before you go and you start purifying this guy and start selling him on the street, just talk to a lawyer. I did a little bit of chatting here and there, and scientists aren't as protected as we think we are, unfortunately. But anyways, seeing that expired lifetime is like candy for me. And side note, I know this is going to be side note after side note. Quite recently, there has been a law passed saying that you can't patent wild-type sequences. So even if this patent were still active today, I do believe it would be invalid, at least in the US. I don't think Canada has passed that same law, but likely Canada will follow suit, at least in that. Likely Canada will follow suit in that particular regard. But anyways, we found the patent for blah blah blah, plasmids encoding restriction enzymes, DPN1 and DPN2. So this is actually a really to-the-point title for patents. Usually they'll say recombinant plasmids in the art known to people who like Streptococcus pneumoniae. It'll be pretty obfuscated, but it's a pretty old patent. But maybe they hadn't figured out how to obfuscate it that much yet. So basically, we are trying to get the sequence from this patent. If you're lucky, there's a whole bunch of images. In 1987, you deserve that patent for cloning that gene in 1987. Okay, in 1987. They would have things like the departmental photographer. If you ask any old-timer, I won't tell you what that is, but ask about the departmental photographer, and you'll get probably some cool stories. But yeah, in 1987, to actually clone DPN1 was a headache. Look at all this. Look at all this stuff. They're doing restriction mapping, that old school style. You know, where am I in the genome of I can say it. I can do it. Streptococcus pneumoniae. Yeah. So basically, cloning this was a bastard back in the day. But, you know, standing on the shoulders of giants and whatnot. There's a couple of, you know, we're not patent lawyers, but basically patents are usually broken down into several sections, and maybe it'll be helpful to actually get the PDF. Save these PDFs, by the way. You never know when you'll lose access to these things. So there are different parts to a patent, just like any scientific paper. And you have, you know, your abstracts, you got your figures, utility statements. That's kind of old, oldie speak. They don't really call that anymore. But you'll have like, why is this invention sort of novel to the art? Why is it important? You'll go through description of the figures, going through that. Background, everything that the anybody knowledgeable needs to know about what you're trying to do. So lots of background about restriction enzymes, cloning, viruses, plasmids. A pretty, you know, we think of it as pretty basic, but all of this stuff has to go into a patent if you're ever filing one. Of course, that's the patent agent's job. Summary of the invention. That's all well and good. So, I don't remember this being so hard. Okay, alright, so we have no sequence here. Yeah, see, I already did this, and probably close to a year ago, but we're just figuring it out together. And this is, you know, when you're trawling through patents, it's never going to be, they're never just going to hand you the sequence, so prepare for a little bit of fun, as we say. So, I do believe the way that I got the sequence, because I don't want just any DPN1 that you can find off PubMed. I want the exact commercial DPN1 that they have here in the patent, and that's what can sometimes be difficult. I don't know whether people are allowed to publish errors in patents. You know, like if you don't want somebody to you know, do what we're doing, you know, you would release a sequence that was wrong and have people chasing their own tail. But I do believe it does have to be correct. Yeah, I forgot DPN1 has all these different, like, genes. It's one of those. So NEB cells, the DPN1 gene from that guy. Okay, that's good. I think we'll use that later. So NEB cells, the version from Diplococcus pneumoniae, not Streptococcus, but it's probably pretty okay. Yeah, I think we'll be okay. So basically, and we're lucky here that they actually deposited the plasmid to ATCC, which is a plasmid repository. Companies don't do that these days anymore, and we know the plasmid name, so I think. Yeah, I think we'll be okay. So let's go find this ATCC. Okie doke, it gives us a gene bank number. Are we almost there? Okay. See, I'm just remembering along with you guys. Do we need both the DPNC and DPND genes? I think it might just be the DPNC. DPN1 endonuclease. I think it's just the DPNC. Okay, but at least we have a sequence. So we have a protein sequence, and ideally right now we would actually have the nucleotide sequence. So let's go to the protein, I guess, entry. And then we can go to, on the related information, we can go to nucleotide, see if it'll give us nucleotide. Okay. And as always, when you're working with like protein cloning stuff, you want to be on the lookout for common features like, beginning methionines and that sort of things, just if things look right the way they should. So, okay, we have the nucleotide, so to select it, we need to go to CDS, and then it'll just highlight it, but then you're like, what do? I can't copy and paste this, right? No, well, you go down here, FASTA, and here we go. Here's the FASTA coding sequence. And again, don't copy and paste it. You can introduce some errors that way. I mean, you can copy and paste this. This is not a big deal, but what you can do is go to send to, complete record, file, FASTA format. Now let's start a little, I started a little folder, PPN1 from patent. Okie doke. And one interesting, so we have the nucleotide sequence for a DPN1 protein, which is nice. So we could stop there, but just for interest's sake, if you remember, we went on NEB, and they actually sell the DPN1 gene from Diplococcus pneumoniae, G41. So let's see what that is. So what I'm trying to do is I'm going to try and find the genome sequence for this, for the Diplococcus. Okay, I can't find it with an easy search. So one way to find difficult to find sequences or homologs or anything like that is BLAST. BLAST is one of my favorite tools to use for identifying, let's say, an unknown DNA sequence, but it's not unknown here, but I do want to see what else pops up in BLAST. So essentially I'm going to use BLAST to see if there are any other variants of DPN1, if there, do we have any nucleotide changes between ours and what's out there. So actually I'm going to shorten this a little bit. Okay, we're just going to leave everything at default, quick and dirty. Highly similar, sure. And then we're just going to give her a go. Okay. Let's see what we see. Okay, so I think we're going to be good with the sequence we have now. We're finding the DPN1 sequence with 100% cover and 100% identity from lots and lots of different genomes. I wonder if they renamed the G41 to something else. But we're not actually getting any hits to Diplococcus. Let's do another BLAST. So let's sharpen up our BLAST tool a little bit. We'll go to organism and go to Diplococcus, this guy, and see what we see. Maybe even relax the stringency a little bit. This is fun. I think this is fun. Alright. Since we've started down this path, the fact that it's giving us Streptococcus instead of Diplococcus means that we need to relax our stringency a little bit. Oh my god. So let's see if this will work. Somewhat similar. Otherwise we're going to have to go into, the dark part of BLAST, which most people I don't think go into. But is Diplococcus the same as Streptococcus? The organism was termed Diplococcus pneumoniae from 1920. Alright, we figured it out. See guys, life, unless you're a microbiologist through and through, and you're just someone that wants to express some protein, you gotta figure this stuff out by yourself. You know, they don't teach you how to do this stuff in class, okay? Okay, all right. So I think we're good with our sequence. Yeah, we have plenty of sequence genomes that match our sequence 100%. So I think we're good to go. All right, so we got the sequence. Yay! We took a bit of a roundabout way. Again, I'm just sort of doing it off the top of my head. So we went from patents. We took a little bit of a sidetrack to ATCC. I guess actually that would be NCBI. Sorry. So we went to ATCC, and then we did some NCBI blast shenanigans just for confirmation. So this is kind of par for the course when you're trying to get some sort of commercial patent. I don't think companies going forward will be patenting their enzymes anymore, just because if you patent something, you release its sequence, and that lets out your sort of bag of tricks. So I think going forward with gene synthesis prices dropping, we're not going to get our information from patents anymore. But at the very least, we got our DPN1 and we're happy. Okay. So we got the DPN1 sequence, so we're good. Now we actually have to design the experiment and how we're going to go through the process to get lotsa DPN1. Okay? Okay. So for the experimental design, we'll break it up into a couple of steps itself. So the first one will be to clone the DPN1. Okay, so basically we have the nucleotide sequence of DPN1. This is double-stranded DNA. Okay, we have the nucleotide sequence, 5 prime, 3 prime, and we somehow have to get it into a cloning vector. And you know, for those curious, I'm using a plasmid that we got from Berkeley. It's macro lab vector. Back when we used to do lick cloning, which we don't anymore, but it was the 1B plasmid. And I just called this plasmid just for short form PML1B. You know, plasmid macro labs 1B. So we can't use PUC19. We need an expression vector, and essentially what it does, it has a T7 promoter. It has your site for inserting, in the old days it was called a multiple cloning site. So it's essentially the place in the plasmid where you insert sequences that you want expressed as a protein. But for that to actually work, you need, you know, your lax stuff in the plasmid. So that's the actual repressor. And basically, usually it's lactose, but in our case it'll be IPTG. It will bind to the repressor. Okay, and then it'll cause the repressor to go away, allowing the T7 polymerase to make a RNA transcript of our, you know, protein we're trying to express. It'll be the mRNA. Although, would it be mRNA? I don't know whether you would get capping in this case. You get some polyadenylation, I think, from the Terminator, but anyways, apparently good enough for translation, because then the actual translation machinery will bind to the RNA, the ribosome. The ribosome's going to bind and make your protein. The question is still, how do we get from here, GPN1, here to there, into that plasmid, into our insertion site? Okay, so my preferred way of cloning, I think it's the most flexible, is I guess overlap-based cloning. So I got my start with lick cloning, I moved on to slick, and then finally I settled on Gibson, Tita, and so on. There's many different variants, but this is the cloning method that we'll be using, and it could be a little bit controversial, but I think restriction enzyme cloning, you may as well spend there's all sorts of like little rules and things that you need to know to use restriction enzyme cloning, and you probably will learn it as part of your training, but very quickly I think you'll move on to lick, slick, and Gibson type techniques for the flexibility, because with restriction enzyme cloning, you are always going to be reliant on having the presence of some sort of restriction enzyme site in your restriction in your expression vector, and then you always have to rely. So it's easy to design those restriction sites into your insert, but you aren't going to have BAM H1 sites all throughout your expression vector. It's going to be in one place, and any sequences upstream or downstream are going to be what you're left with, and that's your lot. So it's good to know how to do restriction enzyme cloning, and there's a couple of variants like gateway cloning, which is pretty powerful, and they use a type of restriction enzyme, but old school restriction enzyme cloning, I think, is slowly being phased out, and for the reasons I mentioned, just the flexibility of where you're allowed to clone into. I wouldn't say it's completely sequence independent. There you can have a whole discussion about that, but it's as close to sequence independent as you can get. But we're going to do these sorts of Gibson Tita-esque techniques. And the way that these techniques work, basically, let's say this is your linearized vector. We'll get how to do that. And I'm just showing it the double-stranded portion of your vector. And we're going to just loop around. So the other part of the linearized vector. Okay, and then our insert, we need to design it in such a way that it has overlaps with the vector that it's going into. Okay, and these overlaps, they can be anywhere between 20 and 40 base pairs, and more base pairs is better for, let's say, 3+ fragment assemblies. Here we're only doing a 2+, so I think anywhere between there will be fine. But basically, when you have these overlaps in, you have these two fragments in solution, you have your double-stranded DNA insert, you have your overlap portions. So this will be 5', 3'. So depending on the mix that you use, Gibson, Tita, whatever, there's some type of nuclease in there, And basically what the nuclease does is it chews back, well, it's a little big, is it chews back one of the strands in a specific sort of direction. So this one is going to be a 5' to 3' exonuclease. I don't know what T5 is, but I think so. So 5' to 3', 5' to 3'. Let's see, 5' to 3', and 5' to 3'. Okay, there we go. So basically these nucleotides from here to here are going to base pair here, and then these nucleotides will base pair here, and then sometimes you'll have a ligase and then a polymerase to fill up gaps, seal everything together. But TITA is nice because it only has the exonuclease. It's nice and cheap. So that's essentially the type of cloning we'll be doing. So now we actually have to figure out how we're going to get these pieces, the insert and the vector, with overlaps. Okay? We're not trying to derive things from first principles, so we're not going to get the little bacteria and, you know, get the sequence out of there through RT-PCR or whatever, or rather just genomic PCR. What we're going to do, and one of the great things about the modern molecular biology landscape, is we're going to do gene synthesis. And it basically solves the problem of, you know, like isolating plus growing the streptococcus, all the sort of biohazardous aspects of that. And we're just going to go straight ahead to gene synthesis, considering that we have the nucleotide sequence. Okay? And the cost, you know, the cost over time has just been, you know, plummeting for gene synthesis, and right now cheapest I've seen is about, you know, 7 cents per base pair US. So let's see, for our DPN1, 776 base pairs, and then let's, you know, add another 50 base pairs of overlaps, so 826. So for, let's call it $58 US, you know, plus shipping, you can have at least the gene fragment of DPN1. You can get the whole plasmid synthesized, so basically cut out the cloning step entirely. So cut out all this assembly entirely. However, usually having it inside a vector, an expression vector, will cost you extra, you know, anywhere from 50 to $100 extra. And, you know, that's up to you, whether you have the time for cloning. We're going to go through the cloning ourselves, though. So to aid with the design of these fragments, we are going to make a sort of in silico mock-up of what the final sequence is going to look like. So I'm going to mock up what I want the final, you know, PML1B DPN1 sequence to be, this combined together, and that will allow us to accurately design these overlaps every time. We'll go through the primer design and everything like that. But first, you can totally do this in Microsoft Word or in Notepad. You can do it, you know, on a piece of paper, but I'm just going to show you the quickest, most direct way to do this sort of thing. There are a couple of different software that you can use for manipulating DNA sequences. SnapGene is very good. However, it is a paid program if you want to actually manipulate the sequence. So the next best free version of SnapGene is Benchling, and it's an online sort of DNA sequence manipulation tool. It's pretty decent. It's a little bit clunky since it is, browser based, but it's always going to be clunkier than something on your desktop just by virtue of what it is. I haven't seen anything that's as good as SnapGene, but it is free. So what I have is the PML1B sequence opened up, and the way I did that is I downloaded the sequence from the Macro Labs website. They have their, vector lists, yada yada, and they have their sequences as well. So I downloaded the sequence, and then I uploaded it to Benchling. And what's nice is it has all the different parts of the plasmid already annotated, so nothing to do there. It's always good when you're looking through a new plasmid just to see what it's got in the plasmid backbone. So we have an ORI, we have our kanamycin resistance, it's got the col E1 origin, got this ROPROM, that's nice. And we have the LAC repressor under the LAC promoter. So this is actually what we need when we were talking about for protein expression. If your plasmid does not have this LAC repressor gene and promoter and I guess terminator, then it won't work for your standard IPTG induction. But as we were talking about before, we're basically going to look at the multiple cloning site or insertion site in the plasmid to see where we're going to insert our DPN1. So here it is laid out here. One important thing, or one useful thing, when you're designing plasmids for protein expression, it's very, very good to have the amino acid translation below it enabled. Then you'll see if you inserted a nucleotide and then added a stop codon somewhere by accident. So in protein expression vectors, I guess traditionally, back from the old days, your first ATG would come from this NCO1 site. It's kind of a blast from the past, but that's tradition is what it is. That's where the first methionine actually, the ribosome binds somewhere up there, and then it starts off translation here. So it's translating way before it even hits your protein. So it's translating. You have a his tag, N-terminal his tag, which is probably one of the most common ways of expressing proteins. And then in this plasmid, it's a little bit of a bonus, depending on how you feel about it. You have a TEV cleavage site, and TEV is enzyme from tobacco etch virus, which actually cleaves between between the Q and the S here. It's a protease, so if you don't want this whole tag on your protein, whether that matters for you or not, then you can cleave it off with TEV. TEV will unfortunately leave one amino acid on your protein, but that's better than maybe 15 amino acids. And then the rest of your protein, of course. And as I said before, this is originally a LIC vector, and again, I think LIC has fallen out of favor because it is, it's kind of going back to the problem of it's not really sequence independent. which is why SLIC was invented, the sequence and ligation independent method. But basically, we have no need for this lick cloning site. Really, I just had this plasmid in the freezer, and it has all the stuff that I need. So we're going to just use it. So first, we have to figure out where we're going to insert our DPN1. So first of all, we have to make sure it's in frame with that first methionine all the way up there. And we want as little additional stuff as possible. So one of the nice things with these sorts of sequence-independent cloning methods is that while you're cloning, you can actually manipulate the plasmid a little bit, just to get a little bit more, bang for your cloning buck. But basically, we're trying to make a in silico reconstruction of what your end plasmid wants to be like. And first of all, I have no need for these lick clonings. Well, I have no need for any additional lick sequences, and I have no need for another stop codon. I think we'll design that in with our actual gene fragment or whatever. So let's do from scratch. So you don't want to touch your original sequence. We're going to make a copy. I'm going to just name it something different. 1B precursor. Let's do something really confusing. So first of all, I don't really care about these annotations for the lick. I'm going to delete that. It's the open reading frame. Delete that. Just simplify our life a little bit. We are going to delete this guy. And actually, it's really tempting to get rid of, sort of cut the fat, as it were, in the plasmid. I'm not sure whether this intervening sequence has any purpose. It's not annotated, but that doesn't mean there isn't some, like a terminator in there. I think the T7 terminator is there, but so I don't know whether this sequence is actually useful, but I think I'm going to just play it safe, not try to be too fancy. I'm just going to get rid of this, excess nucleotides here. I think we can get away with that. So basically, we want our protein to be inserted right after that serine. So the TEV will cleave right here. It'll leave the serine and then your protein of interest. So I'm just going to delete that. Okay. And see the translation automatically picked up like the next open reading frame. Don't panic or anything like that. I'm just going to keep the cursor right there. Okay, then we'll go back to our DPN1 sequence. And actually, I'm going to make a copy of this. And we're going to call it the final plasmid, PML-DPN1. Sorry guys, this is taking a lot longer than I thought. Maybe I think you guys will appreciate the thoroughness anyway. So we're going to go to that new file. We're going to make sure that we're right after that serine, and we are just going to paste in our DPN1 sequence. Now, if we did everything correctly, and if we're lucky, we have our protein that's now in frame with that first methionine. Just so happens that DPN1, the sequence we have, it starts with a methionine, but that's not required. It could start at any amino acid. So you have, it doesn't really matter what this nucleotide is. It's not required for protein expression. This is the important methionine. So you have your methionine, blah blah blah, and then very importantly, you have your stop codon. Here it's a TGA, and again, it was included in this sequence, but if it wasn't there, then you would have to add it manually. Okay, and despite superstition, you only need one stop codon. You don't need to add an additional one. So basically, this will work. If we have, if you had more money than time, which is very good, then you would send this whole sequence to get synthesized. It's a little over 6 KB, so it wouldn't be too bad. I think it would be, $200-300, something like that. But let's say we want to get a whole bunch of proteins made. It's going to be more cost effective for us to do the insertion of the different proteins ourselves. So we are just going to order the DPN1 gene fragment and do the cloning. But anyways, we have the in silico reconstruction of the insertion of the final cloning, and this is sort of our reference sequence we're going to work off of. And actually, before I forget, let me just highlight DPN1 and highlight the open reading frame. Just to keep everything nice and clear. Alright, so we have our sort of mocked up plasmid, and now we have to figure out what sequence we're actually going to get synthesized, and what primers we're going to use to generate our vector. So the insert. Okay, so that's easy. You just send it off and you get it back into a tube. And all is well with the world. So the vector, we needed linearized. And you can either do restriction enzyme linearization. But my preferred method, because it is truly sequence independent, is PCR generating the vector, and then DPN1 treating it. Strangely enough. So vector. So we're going to take this route. Okay. So the insert, we are just going to get a double-stranded DNA synthesized. And we have a choice here of whether we'll have the overlaps that we talked about here, whether we have it on the overlaps on the insert, on the vector, or a bit of both. And for me, that choice basically breaks down into what is easier to PCR. So since we're getting this gene fragment synthesized, you have you're not doing any sort of PCR. You don't have to design primers with overhanging tails to amplify your gene. Let's say if you were doing it RT-PCR, you'd have to design primers that had little tails that were flapping in the wind, like flap, 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 flap. So you don't have to design that and then do the difficult PCR more difficult PCR with these overhangs. And if we have the overhangs on the insert, we actually don't need to include them on the vector. So basically, we are going to, have our vector. We are going to choose a forward primer. We are going to choose a reverse primer. We're going to do some PCR. And we're going to get our, long double-stranded piece. We're not having additional overhangs of the insert on there. It's just going to be all vector based. Okay. But before we get there, let's do the easy part. Let's design the sequence that we want synthesized. that we can send to the company, so we will need to design it with overlaps that overlap with the vector. Okay. What makes this sort of in silico, what makes this process really easy is the in silico reconstruction that you just did, and this is how we want the plasmid to be in the end when it's sequenced and ready to go. This is how the sequence is going to be like when it's ready to go, so it's very easy to design the overlaps. So we're at the minimum going to send the company this sequence, but then remember we want 20 base pairs overlap with where we're inserting into. So we're just going to pick, let's call it 25 base pairs just for luck. We're going to insert the fragment here. We don't have any leeway where we're inserting the DPN1 the 5' end. Like, we need the his tag site, we need the TEV cleavage site. We can't really play around with this, so this is going to be, let's call it the left overlap, okay? So as you can see, it's complementary to the vector, to the left arm of the vector, if you can visualize it. And it'll be synthesized as part of the DPN1. And then similarly for the right overlap, technically you can design the overlap, anywhere you want. Let's say if you deleted this portion and then you designed it to overlap with here, you could trim the fat from the sequence, but we won't do that. We are just going to take this sequence here, and again, let's do 25 base pairs, and let's just call that the right overlap. Now, your spidey sense should really be tingling now, because, this right overlap, where does that actually, because we're going to be doing PCR with primers that are complementary to the right overlap. Where does that right overlap actually occur in our original PML vector? So in our original vector, it actually is right there. And as you remember, we cut out that portion, okay? So this portion will be cut out. We'll have a primer going that way, primer going that way, and we'll be losing this portion. So it's very, very good. You learn it through experience. You need to double and triple check yourself and do sanity checks. But either way, this is going to be the right overlap with the plasmid. And for the sake of synthesis, what you're going to do is you're going to take that, you're going to select that, you're going to select that, and you're going to copy it. And here you want to make sure you're getting the top strand 5' to 3'. So, read it out if you need to read it out. So CCA, TGA, CCA, TGA. Just make sure you're in the right orientation. Never hurts to check. And then we're just going to save that DPN1 for synthesis. Okay. So that's what you're going to send to the the synthesis company, and you'll be like, one of these, please, and then they'll send it to you. Okay, well, that was the easy part. Now we actually have to figure out what we're going to do with this vector situation. And as I mentioned, really we have to design two primers, a forward primer and a reverse primer, to actually make, your polymerase will go around, and then this primer will go around, and eventually you'll just get a whole bunch of strands of your linearized plasmids from this region to this region through the magic of PCR. So we need to design those primers, and again, going back to our in silico reconstruction, this is it can be both simple and complicated, okay? Primer design is just one of those things where you can either spend hours and hours and hours trying to design the perfect primer. You send it off, you get it back, and then it just doesn't work, or it works poorly. And all that time you spent, talking to people, getting advice. Everybody has their old tale of how to best design primers. There's a lot of literature written about it, but you ideally would want to get through this step as quickly as possible, so we won't get too deep into primer design, other than, I suppose, some basics. But there's there's essentially there's the lazy way, and the lazy way will likely work, but your PCR product for the vector maybe won't be that bright. It may not work at all. But the lazy method would be essentially, for the forward primer, we would take the right overlap. We would take the right overlap, and we take the top strand 5' to 3'. That's going to be your, let's call it the lazy forward primer. And then the lazy reverse primer will be the left overlap. And then it'll be, and this is extremely important. I've done this too many times, unfortunately. You want to make sure you take the bottom strand 5' to 3'. So G, G, A, T, T, G. You want to take that strand, okay? So go to Copy Special, Reverse Complement, get the reverse complement. If you click this sequence and you order that, your cloning just won't work. Your PCR won't work. So click Reverse Complement, okay? G, G, A, T, T, G, okay? And basically, this is the laziest way to do it. There's like a good 80, I would say there's like a solid 70-80% chance that will work off the bat, and you don't have to do additional work. But it's always good to analyze your primers. Start with like the most basic primer that you need, without any optimizing, and then you can start paring it down. Primer design is a whole discussion in and of itself, and I find that this discussion, everybody has their own sort of criteria that's been passed along the broken telephone of how to get a good primer. Stuff like stuff that you'll hear. You want anywhere from 18 to 30 base pairs. Old thinking was closer to 18 is good. These days, closer to 30 is totally fine and sometimes preferable. You want TM, anywhere between 55 and let's call it 65. 55 and 65 melting point. I would again, I'm just offering my secret sauce. I would try and get it a little bit higher than 55 to reduce non-specific binding of your primer, but whatever works, guys. Let's not get too crazy here. So about that TM, that size, you want to avoid repeats of, I believe it's more than, so no repeats. Actually, I should say avoid repeats if possible. You won't always have this luxury of avoiding repeats, and in our case, if we have a repeat somewhere in our overlapping arms, well, there's nothing we can really do about it besides inserting it somewhere different in our plasmids. If we have repeats in our overlapping arms, unless we insert it into another plasmid, it's not much we can do. So repeats of A's and T's are generally okay. You don't want to have greater than like 4 or 5 nucleotides repeating. What's really bad is repeats of G's more than 3, repeats of C's more than 3. And that's because G's and C's, they bind tighter. When a G is complementary to C, the energy there to break it is higher. So you don't want to have G or CG. No. You don't want to have C binding because there'll be a lot of G's somewhere in your plasmid, and the primer will want to bind there instead of where you want it in the plasmid. So avoid these if possible. And then the last thing, again, if you can, avoid secondary structure. I think that's how you notate that. Yeah, avoid secondary structure. And basically, when you design a single-stranded sequence, if it's not designed correctly, sometimes what can happen is you can have little loop-de-loops where you can have base pairs in the primer, and basically it will take the primer out of the reaction, or it'll cause the polymerase to extend this primer and waste NTPs and polymerases. So you generally don't want loops. 5' loops are generally well tolerated. 3' loops are generally not well tolerated. So if you avoid them if possible altogether, but if you can't, 5' loops are better than 3' loops. Okay? So this is how I do it, quick and dirty. Again, you could spend hours, just hours designing primers. At a certain point, you have to call it quits, hit the order button, and just go about your life. And another tip for primer design, design more than one set of primer. Sometimes, despite your best efforts in primer design with all these different variables, the primer will just not work due to some unseen case. So what you're going to do, you actually want to design more than one primer. Because, primers, they could take a couple of days to a week to get to you, and that's downtime that you don't want to have. So, if an extra primer is $5, it's worth to have a second primer that you could try right away if the first one doesn't fail. So those are my recommendations. Now, how will we actually do this in this case? Okay, so for TMs, there's many ways of calculating TMs, and Illegal Calc, courtesy of Northwestern University, is quite good. They go into the different calculations of melting point. There's multiple ways of calculating TMs. Don't just take the first one you see. And there's a lot of different variables, like the amount of salt that you have. But again, we're just trying to do this quickly, and we're just trying to get an idea of our primer. So first of all, let's take a look at our lazy primers. Let's see what kind of TMs we get. So, don't freak out. It says anywhere between 64 for the basic calculation, 66, and then salt adjusted for whatever reason is always higher. Again, you can have fun reading all that, but we're just trying to get an idea. This is a primer that melts at a higher temperature, but it's not unusable at all. This is totally fine. It will work. And let's just check the reverse primer, just to see if we're in the ballpark. So see here is an interesting case. The forward primer has a lot of G's and C's, versus the reverse primer has a much lower melting point and therefore lower GC content. So generally you do want your melting points to be close to each other. That's almost a 10 degree C difference, so we'll see if we can't tweak that a little bit. And another thing, so that's, our lazy primers might work. We will have to do a gradient PCR anyway, just to clone everything, but our lazy primers, they was easy to design, but looks like there could be a mismatch of melting temperatures. That's one thing we need to try and fix. We may not be able to. And the second thing we need to do is we need to find the secondary structure. So Sigma has a nice calculator. It's free, called Oligo Evaluator, and it does do secondary structure checking, which is pretty nice. So again, quick and dirty, let's just take our forward primer to look at the structure. Down here, moderate. So let's see what we got. I got a little 5' loop, don't care. 3' loop. So it's not, see here, it doesn't actually tell you the energy, like how much energy it would take to break this. That's not bad. It's not bad. It's T and an A, C and a G, so not great, not terrible. Got a loop in the middle and then the 5' again, so overall not terrible. And then let's try the reverse, and there's nothing, so the reverse is nice that way. So what you would do basically is you would trim your primers both from the 5' and 3' end, depending on what you can get away with, and try and remove any secondary structure. And also you would be trying to match your TMs. So here it gives you the TM. So here it gives you the TM down here in this Oligo Evaluator, and it looks like it's close to the salt adjusted value that it gives you, which is interesting. Again, you can go crazy, but for me, the amount of time spent, you may as well just get 2 primers, and very often, often they'll both work, but the times that you didn't order 2 primers is when it fails. So we have your TM, we have our secondary structure, and here what you would do is you would, for example, let's say I was doing the forward primer, it had more issue. It has a predicted crazy, probably false TM predicted value, like it's not that bad, and it has a secondary structure. Let's just look at that. And basically what we can do is we can delete nucleotides to try and get rid of these guys. And I'm gonna try and get rid of these 4 nucleotides from the end. And what we're gonna try to do is get rid of this TCGA and see if it improves our lot in life a little bit. So we'll take that sequence, copy it, and we'll throw it back into this guy. See what we come up with. Lowered our melting point, and at least we got rid of the secondary structure at the 3' end. So it's something. You can, and then you can, sort of go ham doing that. Now, if you can get access to it, the best program to bundle all of this stuff together is called Oligo 7. And Oligo 7, it's my secret weapon. If you can get it, it's expensive, it's $1,500, but if you can get your hands on it somehow, it's the best primer design software there is, just hands down, or at least that I've tried. So the way that this works, Basically, what I like to do is I like to include the sequence of the plasmid that will be amplifying or linearizing with PCR. So first of all, we need the sequence that will be amplifying, so that's the PML1B original sequence. I'm going to copy it 5' to 3'. I'm going to paste it into oligo7 and just hit the accept button. And it gives us all this information. A lot of it we don't really care too much about. I mean, again, you could drive yourself crazy thinking about this stuff. I think this is a melting curve graph of the entire PML1B plasmid, and then the little red bits and other things. I think those are orths. Anyways, doesn't matter. We don't need that. You can read the manual if you want. So first thing we want to do, I like, if we already know where our plasmids are going to be, I like to start with, the full length unoptimized primer. We go to oligo7, we go to edit forward primer, add our forward primer, hit accept. We're going to edit our reverse primer. I'm going to take our lazy reverse primer. Okay. And if you did everything correctly, the oligo7 should now be showing the PCR product in gray, and your primers, the total length of the PCR product, and as you can see from here, will actually be cutting out with the PCR linearization. We'll be cutting out a small section, as you remember from our design. But let's see if our primers are any good. The lazy primers, the easy way to do this. Basically, oligo7 assigns a score to each primer, of which you can look at analyze key info, selected primers, and oligo7 gives you a score for each primer based on all the little nitty-gritty details you've ever wanted to know about primers. The different delta G's, your 3' delta G. It takes into account duplex formation, so primer on primer, both with itself and with the other primer, hairpin formations, false priming sites, homologies. It takes all that and it boils it down to one single score. And you can go crazy looking at, the duplex formation of your primers and try to optimize that. But again, you don't have all day to agonize about this stuff. Usually it's better to just, do your best, look at the scores, look at secondary structure, and just try that. So here we can see the score ranges anywhere from, 0 to 1000. So the forward primer we knew was going to have problems due to secondary structure. The reverse primer, we already knew it was going to be better. So easiest way that I know to do this, as I said, we're going to start trimming nucleotides. So let's try trimming those 4 from the end. Okay, that did not do anything. It's good to have the primer you're trimming in your clipboard so you can just reconstitute it. Okay, so in this case, trimming the last 4 nucleotides did not do much to improve our score. So actually we are gonna put it back, and we're gonna try to trim the 5' end of the primer, see if it prefers not having this loop here. So we will just trim 3 nucleotides from this. Okay, it's a little bit better. And then let's see, maybe a little bit from the 3' end. Yeah, because now that 3' loop is predominant. So we'll just start deleting nucleotides little by little. Okay, we get more improvement. Okay, what do you think? One more? No. Maybe one from the front, a couple from the back. Okay, so far this is our best one, 21 mer. Melting point is still high, but maybe we can actually increase the reverse one. 21 mer, 707. I'm just going to put that in my clipboard. That's the best one we got yet. And then, I don't know, I don't think we're going to do better than that. TBH, not without getting really, really small. You don't want too small. 20 mer. Yeah. Okay, so again, couple of minutes, quick and dirty. I think this is going to be a primer that's going to be that will probably. I think we've increased our chances of it working, you know, by 10-20%. I'm just going to throw out some numbers. You know, if we were at 70% before, we're probably getting into 80-90%. I'm just gonna call this not lazy forward. Actually, less lazy. Okay, just put that there. And always, when you're designing primers, always double check. So now, where does this you ask yourself, where does this primer land now that we've trimmed it, and will it still work for us? So go back to our original sequence, our in silico sequence of DPN1, and we can see that it'll land here, and it will extend the plasmid forward that way, and it will still work for us even though we're missing nucleotide here and nucleotide here from the overlap, because as we said, the overlap is actually going to be coming from the insert, which we'll have synthesized. So the PCR product the overlap will really only be 24 nucleotides. Right here, it'll only be 24 nucleotides, but that's still plenty. So the vector will be from here onwards, and then the insert will be from there onwards. So we'll still have what we need for accurate assembly. You won't always have the luxury of being able to edit your primers. There are a couple of cases, I won't get into them, where you don't have any leeway in your primers, and that it is what it is. Sometimes you just have to brute force a PCR. So let's get back to our reverse primer, and here, in theory, it's actually a better primer than our forward primer, but if possible, I would like to increase its melting point a little bit, just to try and match that. So we know our reverse primer is 5' to 3' on the bottom strand here. So let's see if we can't increase that to maybe like, I don't know, call it 35 nucleotides. Get the reverse complement. Let's see how we do. It's probably going to be worse. Oh, it's not too bad. Let's see. Slightly lower points, but we're now in the right ballpark for melting point. And I'm just going to trim the 3' end to try match that. See, it's really interesting how a single nucleotide can, affect your score just by impacting small things like, false priming and all that kind of stuff. Yeah, you could spend hours here. Yeah, right. You could be here all day. I think that's good enough. Kind of matching melting points. Matching scores doesn't mean anything. It means they're both equally average. But this will work. Since this is a play along, sing along blog, let's, I'll be actually taking you through the PCRs and looking at gels and all that kind of cool stuff. So it's good to over annotate. You want to make sure you know where everything is when you go back a couple of months from now. Okay, so you could order all 4 of these, but you know what? I think honestly you could probably slam dunk this in one. I said order 2, but this is a pretty easy cloning reaction, so I would probably just order those. But if you're being paranoid and if you're new, you may opt to order, a couple of variants of the same primers. Like, just because I got a higher score on this primer could mean absolutely nothing. Could mean nothing. This could work worse than this forward primer. Okay, that's just the nature of the game. You wish that primer design was more predictable, but everybody has their own sort of secret sauce, and I just showed you mine. It's quick and dirty, and it works very, very often these days. Okay, so basically that's the design part of the, the in silico design part done. We have the gene, the fragment that that we'll have synthesized. Sorry, I keep using the word gene. Someone will definitely call me out on, a gene has all these other elements. Like, I'm just using it casually, let's say. I'm using casual language, science language here. So we have the gene that we're going to synthesize. We have the primer, so that'll be our insert, and then we have the primers that we need to generate our our vector, okay, with the PCR. So the insert, 2 weeks later, you get it in the mail. You're going to reconstitute it. Let's say they send you reconstitute the stock to, just as an example, to 100 nanograms per microliter. Okay. We know that our fragment is, what did we decide? 832 base pairs. I don't know the formula off the top of my head, so I'm gonna go to NAB BioCalc. Then we need mass to moles, 832, 100. So we know that our reconstituted plasmid is 194.5. Let's call it 195 femtomoles per microliter. So you can, if you know the I don't think anyone knows the formula off the top of their heads, but this is what NEB uses, and I think it's well derived. They have their proofs on there. So the vector we have to generate with PCR. So we're going to use the less plasma that you use as template, the less background you'll get on your plates when you plate your cloning reaction. So if you have a lot of colonies on your, your 1 to 0 plate, your vector to insert, your control plate with a vector only, and you have a ton of colonies, it means that something in your reaction here is being transformed. And there's a couple of ways this can happen. Your vector, if you're unlucky, the overlaps that you designed for your insert, if you're unlucky, if they have overlaps with themselves, you can have this scenario. Or if you have leftover template that from the PCR reaction, where you actually got your PCR product, if you don't degrade this will cause high background. Okay. So basically, we're going to linearize the plasmid with PCR. We're going to DPN1 treat. And it's funny that we're purifying DPN1 and we'll need DPN1. We'll DPN1 treat the PCR reaction to get rid of any vector, because this vector will have been isolated from E. coli, right? And the E. coli methylate their plasmid, and the DPN1 will not degrade your PCR product. It'll actually only degrade leftover plasmid DNA. We'll DPN1 the product. We're going to low melt it. So we'll cut the band out of the gel. Okay. We'll cut the band out of an agarose gel, and then we'll use it for coloning. So that's what we're going to do, and I'm going to take you through it step by step. So first of all, the actual PCR. The lower amount of template you can use, the better. I use anywhere from 0.1 nanograms to 1 nanogram of template. You can get pretty awesome PCR products with that amount, especially if it's just vector. Vectors, they tend to have GC-rich portions. Not all throughout them, but they can have them. It's a very good idea to have some sort of GC enhancers. For a PCR like this, you can likely get away with, homebrew fusion. But if you have access to it, if you have the means, this'll do. It's only a, like a 5 kb vector. So homebrew for fusion will do it. Q5, it's expensive, but man, it's the bomb. I'm working on an alternative to Q5. It's probably, or it's likely a Kofu SSO7D, but it's not quite ready to compete with Q5, let's just say. But if you have access to Q5 with GC enhancer buffer, man, does it work well. Enhancer buffer. It works really, really good. Basically, we need to do a PCR with, homebrew, Q5, GC enhancer buffer, whatever. And what I would highly recommend, and it increases our chances with sometimes less than optimal primers, is to do a temperature gradient. So we'll make, let's say, 12 25 microliter reactions. If you don't have a PCR machine that does gradients, beg your boss, find someone on the floor that has one, because they are a game changer. So what a gradient PCR does, you have your 96, I'm not going to draw them out. You have your 96 wells, and then for certain steps of the PCR program, you can actually have a temperature gradient from your position 1 to your position 12. And usually one of the harder parts of a PCR reaction to figure out, you have your 95 denaturation, then you actually have your annealing temperature. And your annealing temperature can be anywhere from, like 55 to 72. And then extension is 72. 72, wow. Extension. Okay, those are your steps, and the beauty of the gradient PCR is it automates this. Instead of doing 12 separate reactions, you make up a master mix for 13 tubes for a bit of extra, make aliquot 12 tubes, put it in the thermocycler, and then run it out on a gel. And I'll show you an example of I'll show you the exact DPN1 gel that I did for the vector, okay? And the gradient on the gel, you can have some interesting things. So it can have no product, no product, no product, a little bit of product, a ton of product, and then as you get to like 72, you get little. Sometimes you could get a little product, non-specific product that will get less as temperature increases. So the annealing optimizing in one round is really awesome. And you're like, Alex, this is super wasteful. Why am I, instead of doing one reaction, why am I doing 12 for a gradient? Well, So for cloning, this type of cloning, you actually need like a decent amount of PCR product because it has to survive through gel purification. I know some people don't gel purify their PCR product if they have a nice product, but generally speaking, your life will be much happier if you gel purify your PCR product. You can, there are people that get away with just cloning straight from PCR product, and that's fine, but a lot of the times when your cloning reaction doesn't work, if you didn't gel purify, that's number one thing to test. So what the gradient will do is it will allow us to optimize the annealing temperature if we need to do the PCR again to get more product, and it will also serve as quite a few samples that we will pool together and then cut out of a gel. So it serves a bulking up reaction and optimization reaction in one. Okay. So let's say I set up this PCR reaction. I ran a gradient. So again, quick and dirty. How would I set up this PCR program? So let's call it 95. We'll do that for, let's do an initial denaturation for 90 seconds. We'll do 95 for 30 seconds. We'll do our gradient 55 to 72 for 30 seconds. And, the rule of thumb for extension is about 30 seconds per kb. It's probably not necessary, but, traditions. Okay, so the vector is 5.3 kb. So for that, 30 seconds per kb, plus a little extra, let's call it, 6 kb. Let's see, that's 3 minutes. Okay, so 3 minutes, or 180 seconds. Okay, and I added that little extra on just in case, there's some high GC rich areas that it needs to plow through. Again, this is how I do it. It may not be the right method, but it's what works for me. Then we're going to cycle for, let's call it 35 cycles, and then do a final extension. I like to do it double the cycling extension time, so do for 6 minutes, and then end. You don't want your PCR machine just idling at room temperature, basically don't idle your PCR machine at all. There's no benefit to it. Just end the PCR program and let it coast to ambient until you can pick it up. And it's okay if it's in the PCR machine overnight. It's okay if it's in the PCR machine over the weekend. You'll have a beautiful PCR product, I promise you. So that's the PCR program we're going to use. Wow, this has taken 2 hours. We're going to need to cut this one down. Jesus. Okay, so here's the gel image, and it's the one that we, and it's where I ran a gradient of the DPN1 vector. I did a couple of other PCRs the same day, but, again, it was a quick and dirty check to see if I was even in the right ballpark. That's about 3, 4, 5 and a bit kb. Yeah, it looks alright. Clearly I was impatient with running this gel, but as you can see, it's good that we did a gradient. We now have lots of PCR product. I only ran every other tube, so this is position 1, position 3, 5, 7, 9, 12. And interestingly, looks like so you have a bit of a trade-off here. You can either have more of your expected product, your desired product, and have some non-specific stuff going on, or have less of it and have less non-specific stuff. So there can be a bit of trade-off with annealing temperatures. But basically, what I did was I took all these tubes, all 12 tubes actually, not just the ones I ran, and sorry, not all 12 tubes, every tube up to, I guess, 1, 3, 5, 7. So I probably took tubes 1 through 8 in our gradient here. Okay, I took tubes 1 through 8, or 8 in our gradient. Okay. Times 25 microliters. That is what, about 200 microliters. Minus however much I ran on the gel. Let's call it, I don't know, call it about 170 microliters of PCR product. Then you want to add, I would say, 1 microliter of DPN1 straight from the stock. And then you need to add Cut Smart buffer, if you're feeling fancy, to 1x. So what's a quick way to figure that out? 170 microliters is 9 parts. Cut Smart buffer is a 10x. So 170, what you do is you just divide it straight up by 9. So we need to add 18, call it 19 microliters of Cut Smart. 19 microliters of 10x Cut Smart. Okay, so then you let your, DPN1 digest. You let it go at 37 degrees for 1 hour, at least an hour or more. You can do overnight. It's not a problem. It degrades all the DPN1. And now comes low melting. You can get away without low melting, but it decreases your chances. There's just other stuff in the PCR mixture that can inhibit your cloning. So I like to go through the low melting step, but before we can go through low melting, we actually need to concentrate our PCR product, because it's, what are we at about 200 microliters total, and to have a agarose gel to load 200 microliters, it's possible. You need a custom comb for it, but it's pretty haggard setup. So I like to reduce this. So what I do is I take that 200 microliters and I do the PCR silica cleanup. So Kaigen sells a version, BioBasic sells a version, everyone sells a version of their PCR silica cleanup kit, but they all work the same with the same buffers, so use whatever you got, or just buy the columns and make your own buffers. So I like to do the PCR silica cleanup. I like to elute, high volume, 100 microliters, and then I know this seems convoluted. It's my way. You can cut out some of this stuff. I concentrate it with the Centrivap. If you have one, man, it's the best. And if you don't, well, elute in I don't know, maybe 50 microliters or something like that. This will get you maximum recovery. So if you elute in 100 microliters and then you concentrate with your Centrivap, it's I'm gonna say close to 95% recovery. It's really good. From a silica column, it's insane. When you're looking at 50, you're only getting about 80%. When you're cloning, sometimes you need every little edge you can get. So you start at DPN1 treated PCR products. We do the PCR silica cleanup. We elute it, concentrate it again, and then we actually low melt it. So you want to use, low melt agarose and low melt silica cleanup. So low melt, if you don't know, it's a type of agarose that melts at a lower temperature, and it's easy to melt. And one little trick, you don't need heat to melt. You don't need heat to melt the low melt agarose. You can just sort of swirl it inside the tube with a buffer, and it will dissolve. We found that the heating actually degrades the performance a little bit. So let me just, show you an example of a low melt gel. I actually didn't take a picture of it for DPN1 because I was that sure. So this is sort of typical of a low melt gel. You have your main band that you want to cut out, and you have usually non-specific bands. If you've concentrated it to this point, you're going to start seeing bands you didn't see before. But so you cut this guy out, put it in an Eppendorf tube, and then add your gel dissolution buffer to do the silica cleanup. And then after that, we're almost there, guys. So this doesn't take as long as you'd think, and the amount of time spent doing this sort of, more involved way is time you'll save by not repeating the experiment. This is a good high success rate method. It may not be the fastest method, but it's definitely a high success rate. So after low melting, you're going to be, again, either, if you have a big band, just elute in 50 microliters, in 50, 30 microliters, or do the Centrovap trick. Okay, and let's say we had a good yield, and our, so we actually have to spec. So get spec, we have to get the quantity of our fragment. So after eluting, after the low melting, we have concentration now. So let's say the concentration we get from the nano drop or whatever you use is 192 nanograms per microliter for your vector. And that's a very good yield from a low melt gel, and that's plenty to clone with. If you're getting sub 30 nanograms per microliter for your vector, you can still do it, but it's grim. You want to be definitely in the 50, 100, 200 nanogram per microliter range. So we know that's 5.3 kb, 59 femtomoles per microliter of our vector. So that's awesome. That's really, really good. You're going to be working with this type of cloning reaction. You're going to be working in the femtomole range, and this is a healthy amount to have. So that's our vector. We know our insert is, 200 femtomoles? 195 femtomoles per microliter. And, already, without any sorts of dilution, if you have 1 microliter of the vector and then 1 microliter of the insert, you already have close to a 1:4 ratio. I mean, it's a little like 1 to 3.8, something like that. But for a 2-fragment assembly, this is a nice ratio, so I don't think we'll even do any sorts of dilutions, assuming you have a pipette that can accurately do 1 microliter. And with a 2-fragment assembly, they're very forgiving. So if you're off, then it's fine. If you're off, you're off. Or maybe we'll even do, to make it easier to pipette. So we're essentially ready to clone. We have our reconstituted insert. We have our purified vector. So in a tube, I'm going to take 5x Steatomix as an example. But you can use 2x Gibson mix or hi-fi mix, whatever. So we have, we need 2 reactions, okay? We need our control reaction, our 1-to-0 reaction. So when I say 1-to-0, I mean vector to insert. So in that reaction, we're going to have 2 microliters of our vector. Let's do a 10 microliter reaction. So it'll be 2 microliters of the theta. It'll be, and then 6 microliters of water. Okay. And then for your, 1 to 4, it'll be 2 microliters of your vector, 2 microliters of your insert, 2 microliters of theta, and then 4 microliters of water. Okay. So you combine those guys, then I think it's 30 degrees C for 40 minutes. And then you transform form 2 microliters. Plate. And look for colonies the next day. So in an ideal world, it doesn't always happen. You have 2 plates, so you're 1 to 0. 1 to 0. And you have your 1 to 4 plate. In an ideal world, you may have a couple of colonies on your 1 to 0 plate. That's, if you have none, that's great. But on your 1 to 4 plate, your experimental plate, you should have buckets. Buckets, 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 buckets. And that's how, that is a good indication that your cloning reaction actually worked. So what you do now is you do colony PCR. And what do I mean by verify our clones? First of all, we want to make sure that basically what we hopefully made on our 1 to 4 plate here, we're going to pick colonies from here and we're going to do colony PCR. Hopefully what those colonies contain is our, basically our in silico sequence and not the original PML1B. Like, we don't want that. Now, how are we going to check that? So we're going to use PCR again. And the best way to do it, I found, there's a couple of ways to screen your clones. That's what we're doing. You can do colony PCR, where you take a colony and you use it as template to amplify your insert portion. And most expression plasmids have the standard T7 terminator and T7 promoter sequences. So often in your fridge you should have a set of T7 terminator and promoter primers, and we'll use those primers to actually do the colony PCR. So for those who don't know, colony PCR basically, and this is literally the whole method. So you have colonies, you pick a decent sized colony, bigger can be better in this situation. So you take it and you put it into, you resuspend it in 50 microliters of water. With that same tip, just have a separate clean plate and have a grid, because you may need to recover, you will need to recover these colonies after. So, take a little, 1 microliter portion that's left in your tip and just dot it onto a new plate, and you can dot multiple colonies on a plate. So you want to either patch plate or start cultures for mini prep. Often I'll start, depending on how successful the cloning looks, from the ratios of the plate. Usually I'll start cultures versus a patch plate, but you can do either or both. If you're feeling confident, then just start, a handful of cultures, like 4, 6, 12 cultures to mini prep. Because by the time that you're finished your colony PCR, then you'll save yourself a day versus going back to the patch plate and then starting cultures. So with that remaining 49 microliters, you're going to boil at 95 degrees C for 5 minutes. Okay. Then you're going to spin at max speed and then you'll know it's working well. You'll see quite a large, a relatively large white pellet on the side. You'll know you had enough cells if you can see a little white cell debris pellet, and then into your PCR reaction you take 10 microliters of that as your template. And then use your T7 primers. Okay. You can also have different primers if they're specific to DPN1, but basically the T7 primer is nice is it'll pick up both this your DPN1 plasmid and your original plasmid, but there will be a size difference in the bands, basically. Alright, I can't find the bloody gel. Okay, so I actually did find the gel. This is the negative control, so plasmid only. If we look at the PML1B vector, we know that the size from the T7 terminator to this T7 promoter is going to be about 262 base pairs, and I know it's a fuzzy ladder, I was in a rush, but if this is 200, then 262 is it's about there. I did a couple of other colony PCR screens while I was at it. Special protein, murine urinase inhibitor, and DPN1. It's interesting that in some of the unsuccessful clones with the other proteins, you don't actually have a complete empty plasmid. You have these weird truncated abominations here and there. But for the DPN1, we got 3 out of 3, so this is what I sent for sequencing. And then we are ready for induction and then purification. But I have been talking for 2.5 hours, so I think that's going to be in part 2. Okay, we'll send for sequencing, and then it's ready for expression and purification. And I think that will be... I haven't even gotten to DPN1 expression myself, so we'll be sort of doing it together, but this is going to be in a different part of the... It'll be in a different video. I've been talking for 2.5 hours. This... When I said A to Z, geez, I mean A to Z. This should be pretty comprehensive, I think. Well, anyways, I hope everyone has a good day, and let me know if you enjoy these sorts of long format educational stuff. No detail spared. I know it's long and grueling, but if you stuck around this long, then clearly you need to hear it. So, hope you have a good day, and good luck with designing your primers.